this video, we focus on bromohydrin formation, a variation of alkene halogenation in which a bromine and a hydroxyl group are added across a CC double bond in an anti-fashion. This process proceeds through a bridged bromonium intermediate and follows Markovnikov type regiochemistry, with the hydroxyl group ending up on the more substituted carbon. Our goal is to walk through the key steps, bromonium formation and the subsequent ring opening, identify which nucleophile controls the outcome, and predict the major product from propane in Aqueous-Br₂. Bromohydrin formation is an anti-addition of Br2 and H2O to an alkene. It's regioselective, with the hydroxyl group adding to the more substituted carbon, following Markovnikov's rule. This occurs because the intermediate bromonium ion allows the nucleophile to attack the carbon with greater positive character. For example, propene reacting with Br2 and H2O yields 1-bromopropane-2-ol as the major product. This product is a racemic mixture due to water attacking the bromonium ion from both faces. A minor pathway can lead to vicinal dibromides if further bromination occurs, or if the solvent is limited. The bromonium ion mechanism achieves both the net anti-addition and Markovnikov regioselectivity. This process proceeds through the same initial bromonium formation, but features a different nucleophilic attack in step 2 that determines regiochemistry and product distribution. Step 1. Electrophilic attack, bromonium ion formation. This step is identical to simple halogenation. The alkene's pi electrons approach and polarize the bromine molecule, making one bromine atom electrophilic. The alkene attacks the bromine, and concurrently, that bromine forms bonds to both alkene carbons, while the other bromine leaves as a bromide ion. This concerted event produces a strained three-membered cyclic bromonium ion that bridges the former double bond. Step 2. Nucleophilic attack, selective backside attack and ring opening. This is where the difference lies. In this reaction mixture, water is present in vast excess and acts as the nucleophile, outcompeting the bromide ion. The water molecule performs a backside attack on the bromonium ion, preferentially attacking the more substituted carbon, where the partial positive charge is greater. This selective attack opens the three-membered ring and produces an intermediate in which the oxygen is temporarily bonded to 3 atoms. After this attack, the oxygen is protonated, and a subsequent deprotonation step removes the extra hydrogen to give the neutral hydroxyl group at the more substituted carbon. Because water can approach the planar bromonium from either face for a prochiral substrate like propane, these pathways lead to both enantiomers and thus to a racemic mixture of the product, 1-bromopropane-2-ol. The bromine and hydroxyl groups are installed in the characteristic anti-orientation. Now let's compare the solvent effects of CH2Cl2 and H2O, showing how each directs the fate of the bromonium intermediate and the resulting product distribution, and then briefly outline practical measures, with a focus on NBS as a controlled bromine source, to minimize byproducts. Solvent choice fundamentally changes the fate of the bromonium ion and thereby the product distribution. In low-polarity non-nucleophilic media, such as CH2Cl2, tighter bromonium-bromide ion pairs and limited solvent nucleophilicity bias the reaction toward bromide-mediated ring opening, yielding vicinal dibromides by anti-addition. By contrast, protic nucleophilic solvents like H2O both stabilize ions and act as competing nucleophiles. Solvent molecules can outnumber and outcompete bromide ion, attacking the more substituted carbon and giving halohydrins with anti-stereochemistry. NBS, which stands for N-bromosuccinimide, is used as a controllable source of electrophilic Br, replacing volatile Br2. NBS releases small amounts of Br2 in Cy2. This controlled release reduces handling hazards and lowers free bromide concentration, helping to suppress unwanted overbromination. Pairing NBS with a large excess of nucleophilic H2O ensures the solvent outcompetes bromide ion and favors halohydrin as the major product. Let's summarize. Step 1. Electrophilic attack, bromonium ion formation. The alkenes pi electrons polarize Br2, leading to the concerted formation of a bridged bromonium ion. Step 2. Nucleophilic attack, selective backside attack, and ring opening. The excess water acts as the nucleophile, performing a backside attack on the more substituted carbon of the bromonium, yielding the 𝑎𝑛-t𝑖 and Markovnikov product. For propene, this gives 1-bromopropane-2-ol as a racemic mixture. Let's organize by keywords. Bromohydrin formation requires bromine and a solvent that acts as a nucleophile, usually water. The reaction follows anti-addition due to the required backside attack on the bromonium ion. The reaction is regioselective because water, acting as the nucleophile, attacks the more substituted carbon. To wrap up, those who wish to deepen their understanding of halohydrin formation and regioselectivity are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.